Thank you. So I'm Eitan Richardson, presenting the work on GANs and GMMs by myself and my PhD supervisor, Yair Weiss at the Hebrew University. So GANs are, of course, very popular. They manage to generate images that are new images that are sharp and remarkably realistic from more and more complex data sets of natural images. Still, it is not clear how well they represent the entire data distribution, and their utility for different inference tasks is questionable. In this work, we wanted to compare GANs to a simple generative model, the Gaussian mixture model. We train, we believe for the first time, GMMs on datasets of full natural images and compare them to GANs in terms of how well they represent the entire data distribution, how sharp and realistic the images are, what you can actually do with the trained model, its utility, and the interpretability of the internal representation. Because of the high dimensionality, measuring how well a model represents the entire data distribution is challenging. To that end, we propose a simple binning-based two-sample test termed NDB. We show that it easily manages to differentiate between the unseen test sets to all samples generated by the different GANs we tested. In addition, it can point to specific cases of mode collapse in GANs. NDB has the advantage of not relying on a representation obtained from a deep neural network that was pre-trained for classification, which is by design invariant to different image properties. We then turn to training GMM on full images, which turns out to be not so simple, again because of the high dimensionality. With the aid of some optimization tricks, we managed to train a variant of GMM called mixture of factor analyzers on full images with training time that is linear with the data dimension. The samples generated by our model are diverse and realistic. We show that they better represent the entire data distribution. They do not mode collapse. However, they are not as sharp as GAN samples. The internal representation of the GMM is interpretable, and it's interesting to see what each component learns. Once trained, the GMM provides simple tractable expressions for different inference tasks, such as likelihood computation and image reconstruction. Finally, we wanted to try and understand why the samples generated by our GMM model are not as sharp as GAN-generated samples. To try and answer that question, we trained a GMM in an adversarial manner and got surprising results. So to summarize, we present NDB, a new evaluation method for high-dimensional generative model. We train a variant of GMM on full images and demonstrate its advantage. And finally, we present interesting insight about generating sharp images from a GMM. Code for GMM training and inference, as well as for NDB evaluation, is publicly available. So if you want to hear more, please visit our poster number 59. Thank you.